Good morning. Continuing with our proof regarding Myhill Nerode theorem for the minimization of finite automaton. We have been discussing what are the equivalences. These three statements are equivalent. Initially, we have proved that 1 is equivalent to 2. Then we have proved 2 is equivalent to 3. And after that proof, I am going to have here we have a finite automaton. Here this is a finite automaton, and as per 2, here we have three equivalence classes J0, J1 and J2. Here we have three equivalence classes J0, J1 and J2. J0 is those strings which take you from Q0 to Q0, and J1 is a set of strings which will take you from Q0 to Q1, and J2 is the set of all strings which will take you from Q0 to Q2. Okay, that means initially J0 is having epsilon because on input symbol, without reading an input symbol, it is taking the same state Q0. That means epsilon is in J0. That means that equivalence class contains epsilon. Now, simply a B, BB, BBB, these are all belongs to J0. Why? If you are accepting a single B, it is staying in the same state, again B staying in the same state, again B staying in the same state. That means B star, that means 0 or more occurrence of B. This is clean closure. 0 or more occurrence of B will take you from Q0 to Q0, Q0 to Q0. And now J1, that means the set of strings which will take you from Q0 to Q1. That means here simply if you give A, that means from Q0 to Q1, you can reach Q1. You are going to have BA. That means for the first B it is staying in the same state, and on the second A we are going to Q1. And now you have say A. This is also A. And suppose that you have a string A. That will take you from Q0 to Q1. Why? Q0, what the first A it reaches Q1, second A it reaches Q2, and for the third A it will come back to Q1. That means, and now you have say B. These are all strings. That means J1 is an equivalence class, and that equivalence class contains these are the different patterns, or these are the language. That means this language is, you call it as say L1, or and now J2, that means the set of strings which will take you from Q0 to Q2. For example, you have A and B A, B A. These are all strings which will take you from Q0 to Q2. So if you study these patterns, then you will show it will show you that means we can assume that J0, all strings which belong to J0 doesn't have any S. That means this only a string of B's. That means 0 or more occurrence of B. That is J0. And this J1, this is having odd number of S. This is having odd number of S. And this is having even number of S. Okay. Now Q1 is a final state and Q2 is also a final state. That means L is a union of J1 and J2. That means L1. That means the meaning of this is it will accept all strings which contain at least one A. It will accept all strings which is having at least one A. That means this is the only non-accepting state. In that non-accepting state, what does it mean? That means it is only having B's. That means if there happens a single A, it will go to Q1 and then it will switch in between Q1 and Q2, and both are accepting states, and so that will be accepted. That means on the first occurrence of A, it will reach Q1, and now for the set of A's and B's, whether it is A or B, no, it will remain either in Q1 or Q2. Okay, that means both are accepting state. That means the language accepted is J1 union J2. J1 is the equivalence class, this class, equivalence class. J2 is this equivalence class. And J1 union J2 means it is the union of these two equivalence classes. Okay. Now I am going to check whether these can be merged. That means I am taking J0 and J1. That means if these two these two are mergeable. So for that, you are going to take a string from B and a string from BA. A string from J0 and another string from J1. You are going to take, and a string from J0 is say BB, and a string from J1 is BA. Okay. Now, after accepting BB, this will be in state Q0, and after BA, accepting BA, that will be in state Q1. The control will be in Q1. Suppose that the next input is say A, and here also we are going to have A. Then what will happen? On accepting this A, this will switch to Q1, and this again will switch to A. That means this will switch to Q2. That means on accepting A, this is going to a final state, and this is also going to another final state. Okay, that means if suppose that after reading BB, the control will be in state Q0, and after accepting BA, the control will be in Q1. And we are checking whether these two are mergeable. If these two are mergeable, we are going to find out. So for that, here I have intentionally put, that means the next string or next input symbol we are going to read is A, and here also we are going to read A. And upon reading A, this will switch to Q1, which is a final state. And upon reading A, this also switches to another final state. Then no problem. Both are moving to final states. Okay. Now suppose that BB on accepting, suppose that the next input is B. Next input is B. And here also after this input BA, you are providing B. That means reading B. After BB, this will be in state Q0. And after reading the next B, again that will be in state Q0, which is a non-final state. Non-final state. Whereas in this case, here BAB, after reading this B, again it is taking the same state. That means that is a final state. That means here after reading, if after reading, we are going to check whether these Q's J0 and J1 are mergeable. That means if these two states can be merged, for that we are going to check after accepting BB, this will be in state Q0, and after that we are testing the first input, which is A. In that case, BBA, and here after accepting BA, the input is in state Q1 and it is also accepting A, and both are moving to final state. In that case it is successful. But we are trying the next input symbol B, and BB, after reading BB, if the next input symbol is B, it is moving to a non-final state, whereas in this case it is moving to a final state. That means J0 and J2 are not mergeable. Now we are going to check whether J0 and J2 are mergeable. J0 and J2. For that, again, one input string from here you have to take, one input string or valid input string from here also you have to take. That means a string from J0 and a string from J2 you have to take. Here I am taking again BB for J0, and from J2 we are reading AA. Okay. Suppose that the next input symbol A, what will happen? Next input symbol A. This will move Q0 switches to Q1, which is a final state, and this J2, after accepting A, if the next input symbol is also A, what will happen? It will move to Q1, which is also a final state. Here the testing is successful, but see here, after accepting BB, if the next input symbol is B, it is moving to a non-final state, and after AA, if it is reading B, it is moving to a final state. Final state. In that case also the test fails. That means J0 and J2 are not. It is not possible to merge J0 and J2. Now you have to check the next one. That means J1 and J2. J1 and J2. Here you have taken the input symbol A from J1 and AA from J2. That means if the next input symbol is A, after accepting A, if the next input symbol is A, what will happen? It will move to Q2, which is a final state, and if the next input symbol is A, again it is moving to a final state, and after accepting A, if the input symbol is next input symbol is B, it is staying in the same state Q1, and again it is a final state, and after reading AA, if the next input symbol is B, it is staying in the same state Q2, and it is also a final state. That means in both of these cases, it is that means J1 and J2, whether it is accepting A or B, it is staying in the same state. So those two states can be merged. That means J1 and J2 can be merged, and the minimized finite automaton is like this: Q0, and this is Q1, Q2, and it is also a final state on accepting A, and this is B, and this is A or B. Okay, and this is the simplest form of this. And now this is RL. That means here you have three equivalence classes, J0, J1 and J2, and here you have RL, which is having two equivalence classes, J0 and J1, J2. Here these are the two equivalence classes. That means RL means here this is the equivalence class RL, and the set L, which is a subset of sigma star, is accepted by some finite state automaton. Then you have partition, that will be a number of states, and the equivalence class denoted by this is Rm, and L is the union of sum of the equivalence class of a right invariant equivalence relation of finite index. That means L is the union of sum of the equivalence classes. Here, for example, L is the union of equivalence classes corresponding to Q1 and Q2, because Q1 and Q2 are the final states. Q1 and Q2 are the final states. So L is the union of J1 and J2. Now third assumption is, or third statement is, the equivalence relation RL defined by X RL by if and only for every Z in sigma star XZ element of L implies YZ element of L, then RL is of finite index. Now here RL is having J0 and J1 J2. J1 J2, that means E is a refinement of RL. E is a refinement of RL means E is having J0, J1 and J2. E is having J0, J1 and J2. That means here in this case the equivalence relation is E. Equivalence relation is E. Here the equivalence relation is RL. Here the equivalence relation is RM. And now E is a refinement of RL means E is a refinement of RL. Now RL is having J0, and these are the two equivalence classes in RL, and E is having J0, J1 and J2 as its equivalence classes. Now the index of E is 3 and index of RL is 2. That means E is a refinement of RL. From this I think you have followed what I have told. Okay, and now we are moving on to the next topic. That means initially okay, now we are now we are going to prove that 3 is equivalent to 1. 3 is here the statement 1 is the set L element of sigma star is accepted by some finite state automaton, and statement number 3 is let equivalence relation RL be defined by X RL y. That means X is related to Y if and only if for every S in sigma star XZ is an element of L implies YZ is an element of L. That means if X is related to Y, that means the equivalence relation is defined by X RL y, and X is related by if and only if Z is some string in sigma star, Z is some string in sigma star, then XZ is an element of L. That means if this language is accepted, then YZ is also accepted. If XZ is rejected, definitely YZ will be rejected. That means either both of them will be accepted or both of them will be rejected. That means if X is related, that means these two X and Y belong to the same equivalence class. And if we are appending or if we are reading another string Z, then what will happen? If X and Y belongs to the same equivalence class, then after accepting Z, either that XZ will be accepted. If XZ is accepted, then YZ is also accepted. If XZ is rejected, YZ also should be rejected. That means that is the equivalence relation defined by XRL by, and this is, and then RL is of finite index. That means RL is having a finite index. Now we are going to prove 3 is equivalent to 1. For that, the proof is like this. RL is right invariant. We are going to prove that RL is right invariant. See, this is called right invariance. That means X is an element of L implies Y is an element of L. That means if X is related to Y, then definitely XZ should be related to YZ. That is called right invariance. Now we have to prove the right invariance of this equivalence class RL. For that, initially By definition, x is related to y if xz is an element of L and yz element of L. That means the double implication. That means if and only if y is an element of L. X is related to y. X. This is the definition. This is the definition. That means x is related to y. If x is an element of L, that definitely implies y is an element of L. That means x is an element of L, then y is an element of L. X is not an element of L, definitely y is not an element of L. That is the double implication. Now, see, x is related to y, and by definition, by this definition, we know that if whatever you append on the right side of x, if you append the same thing on the right side of y, either the both of them should be accepted or will be rejected. Okay, that is the definition of this. And from this definition itself, we are going to prove the right invariance. That is, we are having xwz. That means you are appending wz on the right side of x. Wz. That means you can add a b c b c d or whatever it is. Here you are going to append two strings w and z. The same thing you are going to append here ywz. We are appending. Both are either if you are appending wz on the right side of x, same thing on the right side of y, and as per definition, both of them has to be either accepted or rejected at the same time. That means that is the double implication. That means from the definition you are writing this, and from that you have written this for for all w and for all z. From this we know that xwrl implies ywrl. That means you have to take this xw and here you have to take yw. That means xw is an element of L, w implies yw is an element of L means xw. That means you are going to replace this. From this definition you are defining or you are coming to this. So that means if you have something like this, then from that you will be able to write this. From this you have written this, and from this you are rewriting this. That means if you have such an expression, from that you can write xw rl yw. That means if x rl y, then xw implies xw rl yw means rl is right invariant. Okay, now in the first portion of this is over. That means we have proved that rl is right invariant. Now the second portion is like this: define m dash. That means you are going to define a new finite automaton, and where these are the k dash is a set of states, sigma is the input alphabet, delta is the transition function, q0 is the new start state, and f dash is the set of final states. Now that means from this you are going to develop this finite state automaton for whatever you have written here. That means k dash for each equivalence class of RL. Now we know that RL is an equivalence relation and RL is of finite index. We know that, and here for each equivalence class of RL, we have already proved that RL is of finite index. RL is of finite index means that equivalence relation RL is having finite number of equivalence classes, and for each equivalence class there exists a state in the finite state automaton. Okay. Now we have a state in Q dash. For each equivalence class of RL, we have a state in K. For example, suppose that this RL is having say 5 different equivalence classes, then definitely your finite automaton will be having how many states? 5 states. That is why the number of states K dash is equal to the index of RL. Okay. Now x is an element of sigma star. X an element of sigma sigma star denote the equivalence class X. That means, suppose that you have Q0, Q1, Q2, Q3. Suppose that you have 4 states in your finite automaton. Then the equivalence class corresponding to Q0 will be denoted by Q0, and this will be Q1 in square brackets. This will be Q2 in square brackets, and like that. Okay. And X element of sigma star denote the equivalence class denoted by X. Now, for example, this is an equivalence class. Definitely, this is an equivalence class because epsilon, that is denoted by the equivalence, that epsilon will be accepted by this equivalence class. So, suppose that we have an equivalence class A, then the input A is accepted by, or on input A, it will go to the state corresponding to this A. Okay, that means if you have, say, after reading A, B, C, this also denotes some equivalence class. Okay. And the X element of sigma star denote the equivalence class, this one, X in square brackets. Q0 dash element of epsilon in bracket, that means Q0 dash means the new start state. That means epsilon in square bracket means without reading an input symbol, it is taking the same state Q0 dash. And epsilon is also a valid string as far as Q0 dash is concerned. That means without reading an input symbol, it is reaching Q0 dash state by Q0 dash is the start state. Q0 dash is the start state. And Q0 dash element of epsilon in square brackets and delta dash of XA. That means, suppose that from Q0, upon receiving A, it is moving to Q1, and this is denoted by the state Q0, and Q0 on accepting A, what will happen? Suppose that this is Q0, this is delta dash of Q0 on A is, suppose that this is Q0A. This Q0A is Q1 actually. Q0 is Q1. And likewise, delta dash of this X, that means some X denoted by, this is an equivalence class. In that equivalence class, that equivalence class corresponds to some state, and in that state, if the input symbol is A, it will move to state XA. This definition is consistent because RL is right invariant. That means if we are appending something on the right side, if two equivalence classes X and Y are same, then if you append A here, append B here, what will happen? XA and YB will be same. XA and YA will be the same. That is the right invariance. And this definition is consistent because RL is right invariant. We have already proved that RL is right invariant. Now, delta of XA is equal to XA, which is equal to YA, because X is related to Y. X RL Y. We have already assumed that X is related to Y. X RL Y means X and Y belong to the same equivalence class. That means X on A. That is, this belongs to some equivalence class, and that equivalence class belongs to some state, and that on accepting A, it is moving to XA, it is the same as YA because X is related to Y. That means F dash is the set of finite. Now we assumed that there is a finite state automaton which is accepting this RL is there, and the set of states are K dash. The input output is same. Delta dash is the new start transition function. Q0 dash is the new start state, and F dash is a set of final states. Now, after that, we have proved that the index of RL, this much number of states will be there. This much number of states will be there, and after that, Q0 dash, the new start state we define, and the transitions for these are also transitions for these this new finite automaton also we define, and finally we are going to define the set of final states F dash is equal to X such that X is an element of L. That means those equivalence classes which is accepting the language, and if X is an element of the language you are going to accept, that will be the set of final states. Okay, that means with this the proof of these are complete. That means as per Myhill Nerode theorem, the following statements are equivalent. That means if the set L, or you have an input, if you have an input alphabet sigma, from that if you are generating a string, and that will be accepted if it is accepted by some finite state automaton. And this is the second statement, and this is the third statement. Initially we have proved that 1 and 2 are equivalent. After that we have proved that 2 and 3 are equivalent, and now we have proved that 3 and 1 are equivalent. Okay, now the 3 to 1 equivalency is proved like this. This is very important as far as examination is concerned, and here you have to by heart this proof. And anyway, you should remember this. That means if the for the first statement, if you have a finite automaton, then definitely there will be a language, and that language is accepted by that finite state automaton. Then the language is the union of some of the equivalence classes of a right invariant equivalence relation. That means that language, the accepting language, will be the union of some of the equivalence classes. That equivalence classes belong to the final states. Okay, and after that, this is after that we have proved that from this we can derive RL, and E is a refinement of RL. That means actually E is contained in RL. That means using that we can minimize the number of states of the finite automaton. And after that we proved that from this you can generate a finite state automaton. That is the proof here. You have to study this, and that is the proof, and this proof can be used. This proof can be used for two things. One is for the minimization of minimizing the number of states of the finite automaton, and two for proving certain languages not regular. For example, suppose that here uses of this theorem uses number 1 to prove certain languages not regular, and 2 minimizing number of states. For both of these we can use this, as well as suppose that to prove that these are the two applications of Myhill Nerode theorem. First is to prove certain languages regular, not regular. For example, L is equal to a raised to n, b raised to n, where n greater than or equal to 1. In our pumping lemma session also, we proved this. That means to prove some languages not regular, you can either use Myhill Nerode theorem or you can use pumping lemma. Here I am going to use Myhill Nerode theorem to prove this. Now, suppose that a raised to m is and a raised to n. That means suppose that here I am going to have a square. That means a square means a power 2 means a, and a cube means a, and a raised to 4, etc. Okay, Now, as the number of states are finite, then for some value of this a1, a square, etc. up to a raised to I, for some values of I, this a and a raised to I will be the same, because as the number of states are finite, then this is indefinite. This is infinite. A square, a cube, a raised to 4, etc. up to any number. That means etc. like that. And suppose that you have a number of states for your finite automaton, then the number of states will be finite. And for some value of I and j, or for some value of m and n, for some m and n, a raised to m is equivalent to a raised to n. That means a raised to m and a raised to n belongs to the same state. A raised to m and a raised to n, for some m and n, whatever will be the value of a raised to m and a raised to n. And a raised to m is equivalent to a raised to n means after reading ma, suppose that you reach say state qn, then after reading n states also, n also it is reaching the same state qn. After reading m states it is reaching qn, and after reading n also it reaches qn. Okay, that means that belongs to the same equivalence class. A raised to m and a raised to n are same. Now suppose that I am going to append say a raised to m, if a raised to m and a raised to n belongs to the same equivalence class, then a raised to m, b raised to n, that means after this a raised to m, b raised to n, this is equivalent to a raised to n, b raised to m. A raised to m, b raised to m is equivalent to a raised to b, m, b raised to n. But as per our assumption, a raised to n, b raised to n is, a raised to n, b raised to n is, our assumption is a raised to n, b raised to n is, assume a raised to n, b raised to n is regular. Prove that L is equal to a raised to n, b raised to n, where n greater than or equal to 1 is regular. Prove that a raised to n, b raised to n, where n greater than or equal to 1 is regular. For that, assume that a raised to n, b raised to n is regular. Now you have different languages like a square, a cube, etc. That means for some value of m and n, a raised to m should be equivalent to. That means both belong to the same equivalence class. And in that class, you are appending a raised b raised to m here, and you are again appending b raised to m. That means as this is right invariant, as RL is right invariant, after this if you are appending b raised to m, and after that this is you are appending b raised to m, both of them should be accepted or both of them should be rejected. If this is accepted, this also will be accepted. If this is rejected, this also will be rejected. But as per our assumption, this has to be accepted because it is a raised to m, b raised to m. That means as per a raised to n, b raised to n, both of these are same. So this is accepted, and a raised to m, b raised to n, b raised to n, you can't accept this because n and m are not same. That means for some value of m and n means where m not equal to n. Here the assumption is for some m and n, m not equal to n, a raised to m is equivalent to a raised to n. Then after that you have appended b raised to m here, and b raised to m also you have appended b raised to m here. Then after a raised to m, if b raised to m is there, it has to be accepted, whereas this will be rejected. But this is not possible. This is not possible means if a raised to m and a raised to n belongs to the same equivalence class, then A raised to m, B raised to m, if A raised to m, B raised to m is accepted, A raised to m, B raised to m also should be accepted. But this is accepted and this is rejected. That means our assumption is contradictory. That means it is contradicting. That means our assumption is not right. Our assumption is not right. That means in that way, by proof, this is proof by contradiction. By proof by contradiction, this is contradictory. So L is not regular. This is the proof. L is not regular. So using Myhill Nerode theorem, you can easily prove that A raised to n, B raised to n, n greater than n equal to 1 is not regular. Is not regular. Here the question is like this. This is prove that this is not regular. I tell you this once more. That means initial assumption is our assumption is L. This is regular. To prove that this is not regular, our assumption is this is regular. Okay. Now you have strings a square, a cube, etc. Then I raised to I for some value of m and n where m not equal to n. These two of these a powers should be the same because the number of states are finite. That means we assume that a raised to m is equivalent to a raised to n. That means a raised to m and a raised to m belong to the same class, same equivalence class. After that, as it is a right invariant, you are appending b raised to m on the right side of a raised to m and b raised to m on the right side of a raised to b raised to m. That means after this string, if you are appending b raised to m, after this string you are appending the same. If both a raised to m and a raised to m belong to the same equivalence class, both of this should either be accepted or both of that should be rejected at the same time. That means accepting one and rejecting the other is not possible here, but as per our definition, a raised to m, b raised to m must be accepted and a raised to m, b raised to n is that should be rejected because the value of m and n are different. So from this, that means from our assumption, we have reached a state where this is contradictory. This is contradictory. So our assumption is wrong and the assumption is L is regular and the opposite of that you have to take. That means L is not regular and that is the proof. And with that, I am concluding today's class. And in this lecture, we have proved Myhill Nerode theorem, and you have to by heart that Myhill Nerode theorem. And the uses of Myhill Nerode theorem are to prove certain languages not regular and for minimizing the number of states. Minimization of finite automata we will discuss in the next class. Okay, thank you.